All right, what I'd like to do first is maybe on the exponential section, maybe look at a couple of those. Like, for example, um, somebody's got the book open here to Appendix E. I'm thinking maybe one like 48 real quick. Just make a couple of comments about some things. You had ln square root of e. And you were supposed to simplify that, reduce that, that kind of thing. What did you do with that? What was the key of working with that one? So change that to e to the 1/2. Because if you do that, you can do what with the 1/2? Bring it down in front. Or just understand that ln and e are inverse functions of each other, right? And kind of like if you do square root of 9 and then you square that, you get 9. Square root and square kind of undo each other as inverse functions. That's what ln and e do. So the answer to this is just 1/2. But you could think of it as bringing 1/2 down in front, and then you'd have ln e. And what's ln e? ln e is 1. We talked yesterday about those are a couple of things that we should just have memorized. ln e is 1, and what's ln of 1? ln of 1 is 0. Those two things would really be helpful to you to just know at the drop of a hat. I mean, just automatically, I know ln1 is 0, and I know ln e is 1. Okay? It's very helpful if you know that. If you have to think about those things, if you're not sure on those things, it can make life a little more difficult in some problems, okay, when that pops up. So those are good things to know. Now, you can always think your way through it. You can remember that this is base e to the first is e, and e to the 0 is 1. So you can think your way through those, but it's best if we just know those two facts. Okay, so there's one there. What I'd like to look at here then is number, let's see, the other one I had in mind was, where is it? Number 52, I believe. 52 said log base 2, was it of a? And all you knew was that log base 4 of a was equal to 2.1, correct? So what you would want to do here, and what's helpful to do here is say, okay, what we're trying to do is rewrite this, right? So I'm going to call this x. As a matter of fact, there's a couple people yesterday said on that section, on 39 through 48, that whole section, including all the way to 55, you could do something like this. Say, okay, I'm trying to rewrite this. Well, let's call it x. Because then what I could do is I could say, okay, 2 to the x is equal to a, right? And over here, I know 4 to the 2.1 is equal to a, right? So those two are both equal to a. They have to be equal to each other, correct? Now, what's another way to write 4? 2 to the second. So now I have 2 squared. What do you do with power on a power? Multiply. So this will be 2 to the 4.2. So 2 to the x is equal to 2 to the 4.2. What's x got to be? 4.2. And x, of course, was the thing we were looking for. So this is 4.2. Now, there could have been some other ways to do that as well, but that would be one way to think your way through that using the properties of logs and exponentials that we were talking about. Get a common base. This had a base of 2, this had a base of 4, so the thought process should have been, how can I get those with a common base? Okay? So that's something to think about on that one. I would like to do number 58 real quick with you. 58 says that f of x is equal to 80, but you also know that f of x is 20 e to the 0.1x, right? So we just need to solve this. So this is just a basic solving of an exponential. So we're going to do what to both sides? Divide by 20. This is like what we did in class yesterday. And then what? Natural log of both sides, or just convert it to a natural log, either way. And some of you would probably skip what I just did on the right here, but what do you get on the right? Isn't it just 0.1x, right? Because you can bring the 0.1x down in front, which would leave you ln e. ln e is just 1, right? And so it basically is just 0.1x. and then here you got ln 4, and then we said you could just divide by 0.1. Now, let's talk a little bit about how you give that answer. This would be good enough for me in a problem like this. But there will be times where we will do the calculus stuff, and the calculus stuff will be easier if we had something similar to this. We would rewrite it. It would make the calculus easier. So being able to rewrite these and simplify these is sometimes a good strategy. On this problem, we can just stop right there, and I'm fine with that. Maybe get a decimal or whatever. We talked yesterday how we could divide by a tenth is the same as what? Multiplying by 10. So we could write this as 10 ln 4. That would be acceptable. But there are going to be times where you work a problem like this, and you'll check it on your calculator. It might be a no calculator thing, but you're checking on your calculator. So type in 10 ln 4 right now on your calculator. So you've worked this problem all out. You got 10 ln 4, and you just say, hey, I want to see if I did that right. So you type it in your calculator. Now, you wouldn't type 10 ln 4, but you'd type the original problem or whatever. You might type a solve. Matter of fact, we talked about that, how you can do a solve here, right? But so if you did a solve, the calculator should give you the same thing as if you type in 10 ln 4. So when you type in 10 ln 4, what do you get? Hit enter. 10 ln 4, hit enter. Don't you get 20 ln 2? So what happened? What did it do? 2 squared, right? What the calculator did is it tries to reduce this base. So what would happen is you worked it out and got 10 ln 4, or maybe got ln 4 over 0.1, and then you typed in your calculator, told it to solve it like we did yesterday, and it gives you 20 ln 2, and you think you did it wrong. It turns out you did it right. Here's the other thing that's going to happen on our midterm and on our final and on the AP test. They have a multiple choice section, and so you work all this calculus. Now there isn't any calculus here. That's just pre-calc stuff, but you work all this calculus, and you come down and you get this answer right here, 10 ln 4. And you look at the choices, the 5 choices, and 10 ln 4 is not one of the choices. But 20 ln 2 is one of the choices, right? So not only do you have to be able to do all the calculus stuff they want you, but they're also testing you in that question if you remember some of your pre-calc stuff as well. So you got to remember here that 4 would be the same as 2 squared, and then we can bring the 2 down in front, and with the 10 makes 20, and that's the answer. Okay, so just some little ideas there, but for a problem like that, I'd be good with this right here. That's fine. Okay, one more here, and then we'll get to Appendix D. 64. 64 says j of x equals a e to the kx, and they tell you that j of 1 is what? 5, and j of is 10. So this is a lot like a little bit like 58, a little bit like some of those other ones. What do you think of when you see j of 1? What do you think to do? Plug a 1 in for x, right? Hopefully that's what you think of. Now that's going to be something that will be on our first quiz. We'll talk a lot about that today, about the first quiz and where what we've done so far. That's you have to be able to do what you don't necessarily. You got to be able to read this function notation. So j of 1 means put a 1 in for x. So we get a e to the k times 1 equals 5. And over here you do this. Now you can't really do anything with that. I'm going to rewrite that here. Just a e to the k equals 5. But I can't really do anything with that because I got 2 unknowns. But so do the same thing over here. So I'm going to plug a 3 in for x. So I get a e to the k times 3 equals 10, which would be nicer to rewrite as a e to the 3k equals 10. Okay, so now what we have here, this is nothing different than in algebra when you had 2 equations with 2 unknowns. Remember, we used to do it with lines. Where do they intersect? So if you had 2x plus 3y equals 10 and 4x minus 5y equals 17, what would you do? Get 1 to cancel out. Now, one of the ways to do it was get one variable to cancel out. Another way to do it is solve one of them for y and substitute it into the other one. Remember that? Use substitution. Well, that's what we would want to do here, right? So let's take and solve this one for a. So we just do this. So we just divide by e to the k. So that's what a is. Now we could do the same thing over on the other one, solve that for a, kind of like we saw in that earlier problem. Since they're both equal to a, we could set them equal to each other. Or you could just come in here and just substitute. So we could just take that and plug it in for a. It's just 2 equations, 2 unknowns. That's what you do. 2 equations, 2 unknowns. Okay, solve one, plug it into the other. So now we have 5 over e to the k. We're going to times that by e to the 3k. Now it would be helpful, I think, if we put a 1 under that. Helps me to see it anyway. And then that is equal to 10. So we have 5e to the 3k over e to the k. Right? I'd probably write more than some of you guys would, but it helps me to see it. Now, what can we do with those e's? Well, I mean, we got to be careful about cancel, but it's kind of cancel. What can you do when you're dividing? Subtract those powers, right? Subtract those powers. When you're dividing and the bases are the same, you have 2 bases of each. Subtract the power. So 3k take away k, 2k. So we get 5e to the 2k equals 10. 5e to the 2k equals 10. And now it's just like the problem we just did. Now it's just like 58. We divide both sides by 5. We get e to the 2k equals 2. We do the natural log of both sides. What's ln e to the 2k? 2k. So we get 2k equals ln 2, and we divide by 2. Now another little trick, a little hint I'll give you. When we divide both sides by 2, dividing is usually messier than using fractions. So I will opt to use fractions whenever I can. So when I divide by 2, what I'd rather do is do 1/2 ln 2. That's going to make this easier. The way we write things, and this is why notation is so important, and our first quiz is a lot about notation, understanding notation. The way we write things can make things confusing, or it can make things simple. So in this problem, if I divide by 2, I'd rather write a 1/2 out in front. That's going to make things easy. All right, so that's k. Now you were supposed to also find a. Well, all we have to do now is go back to what we have. We had, what was a? It was 5 over e to the k, right? So now we can plug in that what we just found for k. So we got 5 over e to the 1/2 ln 2. Now for me right now, I would say you could stop right there, okay? But there might be times where it would be to our advantage to be able to simplify a little more. So let's talk about it. So what can I do with this 1/2 in front of the log? Put it in as a power, right? So I could have 2 to the 1/2. What's that? Square root. So down here I'd have e ln square root of 2. What's e to the ln square root of 2? Just square root of 2. The e and the ln undo each other, right? So this whole thing is actually just 5 over square root of 2. That'd be even a simpler answer. And some of you probably remember in Algebra 2 when you used to get rid of radicals in the denominator. Remember that? Multiply top and bottom, and so you could go 5 radical 2 over 2. That's an okay answer too. All right? For right now, it'd be fine to leave that other one. All right? But you can just see how some of those properties can work for you in there. So there's A, and K was 1/2 ln 2. All right, so just some work on exponentials and logs and using those rules and stuff like that. All right, let's keep moving here because I do want to try to give you some work time today, so we got some things to get through. Let's go to Appendix G. Now, Appendix G is all about setting up storage problems. One of the things we will do, Chapter 4 is all about using derivatives, using the calculus that we learned the first half of the year to solve some real-life kind of situation. Okay? And that Chapter 4 we'll probably get into after Christmas. Kind of the last thing we do in the first half of the class, right? The first half is derivatives we talked about, and then we get into integrals. So it's kind of the last thing we do with derivatives. And one of the problems we do a lot of is max and min problems. Okay? So let's look at problem number 4 first. Number 4 is about finding what price should we put on the coffee mugs to get the most profit. That's called the max profit. It's called an optimization problem, and calculus is used for these kind of problems. Well, before you can do the max profit, you have to know what the equation is for profit. And this is where the algebra comes in. You've got to be able to set up an equation for the profit. If you can't set up the equation for the profit, you can't do the calculus. Okay? So that's when we'll have to work on setting up these story problems. Okay? And then they're tough. They are. It's one of the harder things we do all year long, getting these things set up. So they try to help you through it on number 4. They try to do bits and pieces for you. So the first thing they do is they tell you this is the number of mugs you're going to sell. And then they just ask you, why is that the number of mugs you're going to sell? Somebody want to take a crack at it? What's X? What did they tell you X to be? Number of discounts, number of price reductions, right? Let's talk about the problem here. They can sell 1,000 mugs at $1 a piece, right? But if they make them cheaper, sell more, right? And every time they knock a penny off, they can sell 50 more, right? And so every time X goes up 1, the price goes down 1, right? So every time X goes up 1, they add on 50 mugs. So does that make sense, right? So so if X is 0, it means they didn't reduce the price at all. So you sell 1,000 mugs. If X is 1, they sell 50 more. If X is 2, they sell 100 more, right? So that's how many mugs we're going to sell. All right. Then they go to part B. And they've got this, 1 minus 0.01x. What is that? Just that part right there. Price of a mug, right? Because the 1 is the dollar, and the 0.01 is the penny, and X is how many pennies, right? And so that's the price of 1 mug. So that's money we get in. And then what's the minus 60? That's how much it costs to make a mug. So the difference between the money we get and how much it costs us is what? What do we call that? That's the profit. That's the profit, right? So this is revenue minus cost. Basic business concept. Revenue is the money you bring in. Cost is the money, what it makes you to cost you to make the thing. So revenue minus cost. So that's profit of 1 mug. So what's our total profit? Times that by, when you times it by that, because that's a number of mugs. So it's the profit on 1 mug times the number of mugs you sell. So that's the total profit. So we might call that P of X or something, and so that'd be our profit. So now, when we get to chapter 4, they're not going to give you hints like that. They're just going to tell you the situation, and you've got to generate the equation, right? You've got to come up with the equation. But the thought process would be, okay, how many mugs can I sell? I can sell 1,000, but I could sell more than 1,000 if I lower the price. And so that's how you come up with the first one. What's my profit? Well, how much money am I going to get? Well, it's the price. What's the price? Well, it's $1. Oh, but I could knock off a penny though, so I got to subtract the penny. I also got to subtract the cost. So that's your thought process as you go through that. Okay, so then I think you're basically, no, you're not done. They say, so what's the best price? And they give you a hint. They say, well, graph it. See, this is where the calculus would come in. We're going to learn some calculus techniques to take that profit equation and find where it's a maximum. So that's when the calculus would come in right now. All they told you to do is go ahead and graph it. Well, if you did, and we won't take time to do it right now, but if you did get to that point and graph that, it's basically a parabola upside down. So where would max profit be? Right there. And I think it turns out being at 10,450 is the max. Now, it's kind of hard to find it just by tracing because I know you don't see enough decimal places, and we'll get into all that with the calculator later on. We won't take time for that right now, but that is the thing. So what does that tell you? What's the best price? 90 cents. So the max is when they have 10 price reductions, so they should sell them at 90 cents according to this information. Okay? All right. Yep. Number 11. Number 11, this is one of my favorite ones. You know, you picture this guy stranded in the snow. He's got to get to safety. So the first thing he does is whip out his calculus to determine which route he should take, right? So not the most realistic example, but he's 6 miles away from a service station. He's 3 miles deep into the snow here, and, you know, what should he do? Well, he could walk directly. That'd be the shortest, but what's wrong with that? Slow, right? In the snow, he's going to walk slow. He could go up here, which would be longer, but it's faster, right? Because he gets to walk on the road, and he can walk faster on the road. It's kind of like when I go to Grand Island. Should I take Highway 30? Should I take the interstate? I go faster on the interstate, but it's shorter if I take Highway 30, but I take the tab, whatever. So we want to find the minimum time is what we're interested in. Where should he go to do the minimum? Because he could do those two things, or he could do some combination. He could go here somewhere, right? Somewhere along there he could go. So those are all the different possibilities. So what we want is some time, and then R, they tell us, they give us it to use R. They say let R be how far he walks on the road. So I think you got to draw a picture here. So in my picture, this would be R right here. Right? That's how far he'd walk on the road. Now, if R is 0, what's that mean? Straight to the station. If R is 6, he went up and then this way. Now, did it ask you about domain and stuff in there? Yeah, it did. Did it ask about domain? Not on this one. But that would be your domain on 6, right? What's the smallest? Domain is the inputs, right? And in this problem, R is going to be our inputs. So what's the littlest R could be? Well, that'd be if he didn't walk on the road at all. And what's the biggest R could be? Would be 6, right? Because that's if he went straight up. Well, he could have went backwards, but that'd been silly. But, right? Of course, this whole problem's kind of silly, so what the heck. But if R is 6, so that's kind of the biggest it could be. So if we're talking about domain, you know, that would, we might think of that. Okay, anyway. Back to this. Now, what about this piece of my triangle? What can I label that? Wouldn't that be 6 minus R? Right? If the whole line is 6 and this piece is R, the other piece has to be 6 minus R. Okay? All right? And then that would allow me to do the hypotenuse here, right? Little Pythagorean theorem. So it'd be 3 squared plus 6 minus R squared, and then be the square root of all that. Now, somebody in the other class was asking me, they said, well, if you square root that, can't you just get 3 and 6 minus R? No, be really careful about that. Here's a quick example. Square root of 4 plus 9 is square root of 13, correct? Everybody agree with that? Square root of 13, and that's like, I don't know, decimal. Square root of 13. If you try to do the square root of each piece, you get 5. That's not the square root of 13, I think, right? So when you have a sum like this, and you square root, you can't square root each piece. Okay, so we can't square root each piece of it. Okay, so we just have to leave it like that. All right. So why? Okay, so I'm labeling all this pieces here, but what I'm trying to get is a time equation. So let's think about this. Distance equals rate times time. So how do I get time? Well, that'd be distance over, I better write out rate because we're using R for something else here, so I got to be careful. This is rate, and this is time. Okay, so I have distance equals rate times time. So time would be distance divided by rate. Everybody okay with that? Distance divided by rate. Okay, so now the time it takes this poor guy to walk in the snow or to walk to the gas station is going to be his time in the snow plus his time on the road. Okay? All right. Time in the snow plus time in the road. Right? So what's his time in the snow? Well, it'd be his distance in the snow, which is that right there. That'd be his distance in the snow divided by his rate in the snow. What's his rate in the snow? 3 miles per hour. So distance divided by rate would be time. So this is his time in the snow plus now his time on the road. Well, his distance on the road is R. And what's his rate on the road? His rate on the road is 4. So the rate on the road is 4. So that would give him the time on the road. So those two added together would be his total time. So here we go. So see, there's no calculus there, right? I mean, the calculus would come in math. We want to find the minimum time. So we want the minimum of that function. We want to know when that function's at its lowest. And calculus techniques will tell us that. Okay? But if we can't get to this point, we can't do any of the calculus. Right? Luckily, this is not a huge part of what we do all year long. This is one of the harder things we ever have to do is get these things set up like this. Okay? So don't worry too much about it, but it is something that we want to be able to do, but is sometimes tricky. All right, last thing I want to talk about is number 20. Okay, And I just want to talk about the kind of the technique. Whenever I read a problem like 20 and I see all these different units, I think about what you sometimes do in chemistry, I think, or in science class. We want to get an answer that's dollars per mile for this trip. Okay? That's our final answer. So that's our cost. And it's supposed to be in terms of V, the speed. So it'll be a function something like this. So it'll have V in it. V will be the variable. And we went dollar per mile. So I start looking at what they give me. They tell me that gas is $1.50 a gallon. This book's a little old, obviously. They tell me that the driver gets paid $15 an hour. The speed is V miles per hour. And then what's that? 180 minus 2V over 7 is miles per gallon. So I got all these units, and what I'm going to do is try to get those to add up to this. So we're trying to get the cost. Now it occurs to me that the cost of this is going to be the cost of the gas plus the cost of the driver. Does that make sense? It's going to be the cost of the gas plus the cost of the driver. So the cost of the gas is $1.50 per gallon. And then I'm just going to do this with my units. Right? I like the old chemistry thing. So I want to end up with dollars per mile. So is there a way I could get gallons to cancel and have miles down here? What would I use? The miles per gallon, which was this right here. But I'm going to have to flip it, right? Because this is miles per gallon, I want gallons per mile. So I'm going to need the 180 minus 2V down here. I need the 7 up here. And gallons will cancel, and that'll be the cost of the gas in dollars per mile. Now I need to add to that the cost of the driver. Well, the driver gets $15 an hour. And I use that because I know I want cost on top. So now I need hours to cancel. So what could I do? I want miles and hours. So that'd be V, right? See, now I can get hours to cancel. So where's the V go? I got to flip that, don't I? So V's got to go up there, right? So I got V miles per hour, so I flip that. So whenever I see a problem with a bunch of units like that, I think sometimes the best strategy is think what units you want to end up with, and then think about how you have to multiply to make that happen. So it's basically, we could multiply here, that'd be 1050 over 180 minus 2V, that's the gas, plus 15 over V, that's the driver. There you go. So that's how you would divide it. I think that's the best strategy on that. Okay? All right. So let's move on to the front of the book, page 1. And while you're doing that, getting ready, there'll be some things you probably want to write down. I'll just talk to you a little bit here about our first quiz. The first quiz will be over the first 3 sections. And it's mostly about functions and function notation and reading graphs, writing some equations. Most of what we've done so far is not really on it. I mean, think about what we've done so far. The exploration stuff we did was looking ahead, looking out there for where we're headed, what we're going to do, in the things we're going to be studying, integrals, derivatives, that stuff. None of that's on this quiz. Then we've also done some review. We did some exponentials and logs. I mean, there might be a little bit with that, but not anything specifically. But I might give you a function that has an exponential in it or something and ask you some things about it. But it's going to be mostly no calculator, or all no calculator. But it's not going to be like Appendix E was, where I'm just telling you to solve these exponentials. It's not that kind of stuff. Okay? So those were kind of review things. Now, the graphing lines, or being able to write a line equation, we're going to see an example here. We've got to be able to do that. But mostly the quiz is going to be stuff we do starting today. Okay, starting today. So we've reviewed some things. We've kind of looked ahead to see where we're going to go. Now we're getting into it here in Chapter 1, and we're going to start rolling along.
Okay? So if you turn to chapter 1, it talks about functions calculus style. It just says, okay, this first section is just about, because I told you, calculus is all about functions. Working with functions, being able to read and write in the language of functions. So, the first thing we'll talk about with functions is graphs. So if you turn over to page 2, you'll see a couple of graphs right here. And these are graphs, it says at the bottom of page 1, it says, imagine you had a hot air balloon floating above the Kansas prairie. Here's a graph of its altitude. So we have an altitude function and a graph of its vertical velocity. Okay? And there are functions. And so part of what I want to do is ask you some questions. You want to be able to read a graph. And what is the graph telling you about that situation? Okay? So this is a balloon. So imagine, close your eyes if you want to. Picture this balloon. Okay? Now you got to open them and look back at the graph again. Now look at the graph. Picture the balloon that graph is describing. So what do you imagine the balloon, what's one thing the balloon you know is doing? Going up and down. Right? Now did anybody picture the balloon also going horizontally? Okay? Could it have been just going up and down? Based on that information, the balloon could have just been going up and down. Right? It wouldn't have had to have been going horizontally. This is all just about altitude and vertical velocity. Okay, so it could have been just moving up and down. Okay, but that's what it's doing. It's moving up and down. All right, so let's look at these two graphs. And these two graphs have some connections between them, which is good. So this is the altitude graph. Let's say that's A. So if I just asked you a question and said, what's A of 4? What would you have said? 4,400 feet, right? You're just reading the graph. What that's saying is when you plug in a 4, when you have an input of 4, what's your output, right? And you just read off the graph, it's about 4,400, 4,500, maybe somewhere there. Sounds good. So if you're doing that, I have to accept a range of answers, probably, right? You're just estimating up there. Oh, that's the best you can do. That's all the information you have, okay? If I said something like this, solve this equation, if I said solve that equation, what would you be looking for there? When the y value is 5,000, right? How many times that happened? Twice. So there'd be two solutions to that, right? Maybe one's about 0.5, the other one's about 2.1 or something. So that would be t. So it'd be t equals 0.5, and maybe when t equals 2.1. That's when the balloon is 5,000 feet high. Okay, so those are, when I say the language of functions, it's simple. Right? Hopefully that's very simple, right? Something like that would be an easy question. All right, some other thing, then we can do the same thing over here, right? Ask you for something. Now you notice this has some positive and some negative values. When the graph is above the x-axis, it's positive. Its y values, its outputs are positive. When we talk about what a function is, we're usually talking about its outputs, right? When we say the function is positive, we're talking about its y value are positive. Okay, so when it's up here above the x-axis, you got positive y values, down here negative. Okay, let's look at some corresponding points. In other words, what do you think of on the balloon when you think of these points? It's stopped. Right? Remember we talked about the door swinging open? These are like peaks, right? As far as it's going up, then going down, or going down, then starts going back up. It's stopped. Doesn't that correspond to these points here? Right? Which, of course, is when the velocity is, the outputs are 0 there on the x-axis. That makes sense. When it's stopped, the velocity is 0. So those peaks correspond with where that graph crosses the x-axis. Okay? Interesting. What about when this graph has peaks? Say it again. Well, if it's moving at a constant velocity, wouldn't this graph be horizontal? I mean, I don't. Well, at that instant, okay, it's changing from an increasing velocity to a decreasing velocity. I would agree with that, right? But it's so. But what would be another word we could say? What's it? Well, I don't even care about this graph right now. I'm just talking about what's the balloon doing. I don't think I've heard what I'm looking for. Minimum, maximum be okay. It's changing. What's happening with the balloon at those points? Starting to slow down or speed up. I think at those points, I actually think at those points, at all three of those points, it's starting to slow down, isn't it? At all three of them, it's starting to slow down, isn't it? Because at every one of those, the velocity is starting to go back to where? Zero. If your velocity is starting to go back to zero, aren't you slowing down? Okay, so with that, what's happening at those 3 points? Isn't that when it's going its fastest in that little time period? Wouldn't that be true? I mean, if that's the point when it starts to slow down, isn't that when it would be going the fastest? Right? Because now remember, negative velocity means it's just going down, right? And positive velocity, these up here, is when it's going up. But these little peaks are when it's going its fastest. Now, what do those correspond to over here? Well, this first one is just a little bit after 2, so that'd be right in there. Does that make sense? That right there, it's going about the fastest? What would you say about that point right there? I think I heard it, Robbie. I think you said it. Steepest. Isn't that when this graph is the steepest? Because it doesn't look like it's getting steeper, 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 and then all of a sudden it starts to level off again? Because it's slowing down, right? It's going steeper, going steeper. Remember we said that with the door. When this one's the steepest, when it's going the fastest. Okay, so steeper, 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 then start to get a little less. We've actually got a name for that. It's called inflection point. When the curvature of this is starting to change. Okay, and then that happens again about right there, and it happens again about right there, and that would be those red dots. Okay, so the point is, there's a lot of information about what the balloon's doing here in these points. But we want to be able to, like I wrote up here earlier, understand the language of the graph, be able to read points off the graph, and tell a little something about what's going on. Okay, let's move along. At the top of page 3, we have a function. Sometimes you have a function just from data. So here we have a table. You know, the title of our book is Calculus from a Graphical, Numerical, and Symbolic Points of View. We look at different functions that are given to us in a variety of ways. Could be a graph, could be an equation, could be a table of data. So here's a table of population. Now we know there's some populations in between there, but here's a table of some. So then they've graphed those points. And we would probably connect those dots because, again, we know there are populations in between there, not just at those 10-year or 100-year marks or whatever they are. Okay? So that's a function. Turn to the top of page 4. Now, at the top of page 4, you have a function k. Now, the difference in this function is all we have is this table of data. We don't have any inkling what it's about, like the one on the other page was the world's population. Here we just have some numbers, no context whatsoever. So if I gave you on the quiz, if I gave you that function k, and I asked you, what's k of 2, you would say what? You would say 8. Easy. If I said solve this equation, k of x equals -9, what would you say? X equals -2 would be a better answer, right? X equals -2. So just inputs versus outputs. On the one they said what input gives an output of -9. The other one is input of 2 gives what output. Okay? Now, trick question. Not really a trick question, it's a very legitimate question. What's k of 5? Don't say it right away, just think. What's k of 5? Anybody got an answer? Say that. 1 5/8. Anybody else got an answer? Okay, well, let's talk about a few other things and give you a few hints along the way. Let's imagine I had this function. Let's go back to something we're a little more familiar with. Okay, I got this function right here. And I ask you, what's the domain of that function? We call that the natural domain. Sometimes I give you a function and I give you a domain. I'll say, hey, we're going to look at the function x squared from 0 to 4. And so then in that problem, 0 to 4 is a domain. But normally x squared has all reals as a domain. You can have anything. But sometimes I give you a domain. So what's the domain of this? The natural domain 3 over n. All reals except x equals 0. Or we could have said such that x does not equal 0 or something like that. We could have said just x can't equal 0. We could have done this with our new notation. We could have said negative infinity to 0. We could have said 0 to infinity. That would include everything but 0. Right? That's the domain. Okay? And why can't x be 0? You can't divide by 0. So what that means, the reason 0 is not in the domain is because when I put 0 in, I don't get an output. Would you agree with that? For any other number, I can put it in for x, and I can get out an output. But for 0, I don't get an output. So what do we say if I ask you f of 0, what would you write for your answer? You would write undefined. Now, you wouldn't write undefined because you can't divide by 0. You would write undefined because that function does not have an output for an input of 0. Right? Defined means a definition. A function is a rule which defines the function. It tells you how to get the outputs. There is no output for an input of 0, so we say the function is undefined at 0. So let's go back to this one. What's k of 5? Undefined. Now, I know what Ryan was doing. He was looking for a pattern there of the y's, and he was trying to fit things in and so forth. In that particular function, the domain was simply those, 8 numbers? That was the domain of that function. -3, -2, -1, 0, 1, 2, 3. That was the domain. There are no other numbers in that function. We can't assume, we're not assuming anything. So k of 5, there is no output for that input. So we say it's undefined. So this function's undefined for a lot of things. Okay, so it's a little different way of looking at it. We're not used to that. We're used to equations. We're not used to tables of values, a table of values. So k of 5, we would say, is undefined. There is no output for that input. Okay, next one there, example 4. I can promise you that on the quiz next week, there will be a problem like that example 4. Piecewise functions. You guys wrote those course description questions. Many of you said in there that piecewise functions might be something you need to brush up on. Here we go. So, you might want to jot this down because there will be a problem like this. There will be a graph with some lines and some partial circles, and you will be required to write the piecewise definition of that function. Okay? So let's do it. Now they've already got the answer down at the bottom, but we'll pretend we didn't see that. So they call this function m. Now the way you write a piecewise function is you just put kind of a curly bracket. That's a terrible curly bracket, but doesn't matter. And it's called a piecewise function because it's just in pieces. This graph has 4 pieces. It's got a piece of a line, it's got a half circle, it's got another piece of a line, and it's got another piece of a line. So all we have to do is write the equation of the different pieces. Now lines are easy. I hope. We talked about this the other day. Here's how you write the equation of a line. Right? The old point-slope form. So that is something you're going to need to be able to do on this next quiz. All right? So let's do the lines first because those will be easy. Then we'll talk about the circle. So this line, we need to... Now, another comment. Here's your y equals right here. We already have the y equals right there, so we're not going to include that part. We just want the part that comes after the equal, okay? Because that's the y equals right there. So what's the slope of this line? -3/2. Parentheses. Now let's just pick a point. How about this point right here would be a good one? So that'd be x minus -3, so that turned into x plus 3, plus 0, right? You have to write the 0, just emphasize that, right? So we got the point -3, 0, so we plug that into there. Okay, so that's that piece. Now we also have to tell how big is that piece. And we're talking about domain here. We're talking about the x value. So this piece goes from an x value of -5 to -3. All right, and we'll go ahead and include both of those. Now, some people might say, well, what about -infinity? Doesn't that line go on forever? If it would have had an arrow on it, and we wouldn't have this grid where it's boxed in like this, yeah, then we might have said -infinity to -3. But since it's boxed in, there's no arrow there, we'll just go -5 to -3. And I'll include the -3, and then I won't include it on the circle. How about that? They should be included in both pieces. Okay, include in one, maybe not. Let's skip the circle for right now. Leave a space for it. Let's do this line. What's the slope? 1. And let's just do that point right there, 1, 0. So it'd be x minus 1 plus 0. And then that's going to go from 1 to 3. And we can include the 1 and 3. So we won't include the circle in at all. All right, and now let's do the last piece. Slope is 1. Let's do this point here at the end. I like those 0 things. So x minus 5 plus 0. And then that goes, oops, we shouldn't include the 3 this time, because we included on the other one. 3 to 5, and we should include the 5. Does that make sense? Okay, which that's not bad. I mean, it's just, especially when they're lines, right? When they're lines, we just do this whole thing, and then we just have to do where the piece is from. And we're doing it from left to right. So now we got to do the circle. All right, so we do have to, this is probably on our quiz of all the things, this might be one thing you're going to have to study up on a little bit. Here is the equation of a circle. Right? That's the equation of a circle. And what's H and K? The center. And R, of course, is the radius. So in that picture, where is the center? -1. Yes. -1, 0. And the radius? 2. So we would have x plus 1 quantity squared. I'm going to go ahead and write y minus 0. You might do that just, and I'll tell you why, because you're not always going to get lucky enough to have a 0 in there. And so it might have been a 2 or a 3 in there, and so that way you can see how this would look if that number's in there. So I'm going to leave the minus 0 as I work through this. Now, we can't just take that and stick it into the piecewise function. Why not? Well, yes, it's only half circle, number 1. But number 2, it's y equals, right? So we need to get this circle equation solved for y. So we need to go into here and solve this for y. So we need to subtract the x quantity, and there's no good reason to FOIL that out. Just leave it as a quantity squared. What would I do at this point? Square root both sides. Now when you square root, you need to do plus or minus. See, that's the top half, that's that whole circle business here. And remember, when we square root this, we can't square root each piece, right? So we can't square root the 4 and square root the other thing. We got it just like that thing we were talking about a minute ago. Okay, we get a plus or minus thing. But the plus or minus is talking about the top and bottom half of the circle, see? That's the plus minus. Plus is the top half, minus is the bottom half. Which do we want? You remember the old vertical line test, right? The circle would not be a function, right? For a function, one input, one output. And so we just have the bottom half. So we only want the negative piece of this. So we go back to our problem and we put it in. So y equals, and this would be negative square root 4, was it minus x plus 1 squared? And then that goes from -3 to 1. And then I wouldn't include the okay, does that make sense? So you got it, you circle equation, put in your center, put in your radius, solve for y. Top or bottom half you have to consider. Now what if it only would have been a quarter circle? What if it only would have been this? From here to there. What if we'd only had that quarter circle? Would that have changed this equation? What's that? It would just change this number here. You get what I'm saying? You got this quarter circle, you're still the bottom half of the function. The only difference is it only goes from -1 to 1 now. So right here you would just go -1 to 1. So any piece of the bottom that you have, it's the same equation. It just, how big of the piece is determined by this over here. Yeah.
So why don't you include the same point in two different?
You know, it's not a huge deal. Especially when, because what might happen is you have one goes like this, and then the other one takes off like that. So then you definitely would. But here, when they're both taken off from the same place, to be honest, if you do, it's no big deal. Yeah, so if you included them there, that'd be okay. But I might give you one, like I said, where there's a gap or a jump there, then you would want to do, if it's filled in, you'd include it if it's a hole. Okay? All right. So that is something for sure you want to be able to do, and there will be one of the homework questions is on it. Okay, so we're getting pretty close here. If we turn to page 6, is the clock working? Okay, kicking right away. All right. Seems like we got a lot of time left, but that's okay. All right, so if you look at page 6 talks about just some of the different types of functions we can run into. And so it just kind of goes through there. So it has function f. It's just a regular old equation, algebra type function that we're used to working with. G is just written in words. Sometimes you have a function that's just written out in words, like the human population in T years. You have a piecewise function, which we just got talking about right there. Or you could have a function that's just a graph. You don't have any equation or any other information, it's just a graph. If that's all you have, you just read off of that. K, sometimes you have a function that's just a table, just like we talked about earlier. All right. So then you get into, on chapter 7, talks about a rule. Of course, that's what defines the function. How do you get the inputs turned into outputs? What's the rule? That could be an equation, could be a table, whatever. The domain is your possible inputs, and your range is your possible outputs. Okay, and there'll be some questions like that. And of course, remember that a function only one input, or for one input there can only be one output. That's the old vertical line test sort of thing. And I guess maybe there's one other thing that I mentioned to the other class. And it had to do with this square root thing we just talked about here. And that was, if I ask you for the square root of 9, what do you write?
It's just 3. It's 3.
Just 3. It's just 3. And you're confusing that with this question. Solve x squared equals 9. Well, then you do what we were doing, which is where you square root both sides, but when you square root both sides, you're asking for both the positive and the negative square root of 9. So that's why you get plus or minus 3. But in this problem, they're just asking for the positive square root of 9. So it's just 3. Okay, so if I have this function right here, the square root of x function, that is just the top half of a sideways parabola, because it's only asking for the positive output, the positive square root. Okay, so that's something that comes up from time to time with this. So whenever we're doing a square root in solving an equation, we have to tack on that plus minus, because we're asking what values of x will solve this. Well, 3 and negative 3 will both solve that. But here we're just asking what's the positive square root of. So two different questions. All right, let me go through here and see if I'm leaving off anything. I don't think so. Okay, so your homework tonight is section 1.1. HQ stands for homework questions. That's off of your packet. And then also, I've got this scavenger hunt, calculator scavenger hunt. So it asks you to do different things in your calculator, go through it, and find out different things for your calculator. And that we are going to hand in on Friday. So that will be due on Friday. And I'll pass that around here. And at that point, you may work on your homework. You can move around and work in little groups if you want to, work by yourself, whatever the case may be.